Here's another video of the lecture Intro-PD. In this lecture we present the first part of section 3.1. So we don't present the full section 3.1 but only the first half. This section is called Green's function, and Green's function is a method to determine solutions on. So we look for solutions. We present a method to construct solutions of Poisson's equation. So minus Laplace u is equal to f on omega for some open and bounded domain omega in R n. So this is what we do, and in the first part, we first present some further conditions which uniquely determines, I should say differently, further conditions such that there exists at most one solution. Yeah, because we want existence and uniqueness. Yeah, so we present some further conditions which allow at most one solution. Yeah. Then the construction of a solution shows existence and uniqueness. And this is what we are interested in. Okay, so let's start. First, we need some formulas. We need so-called Green's first formula and Green's second formula. They are rather easy. Yeah, we apply the divergence theorem. First, we have two functions, twice differentiable. And now we say, here, this I omitted, we say this means, it's continuously differentiable on a closure of an open subset. This means u and v belong to continuously differentiable, twice continuously differentiable on omega, and all partial derivatives of order less or equal to, including the function itself, extend continuously to the boundary. So they extend continuously to the closed subset omega, to the closure of omega. The closure is of course omega union with the boundary, by definition of the boundary. Okay, so this means continuously differentiable on the closure. This means all, also twice continuously differentiable, so this means all partial derivatives of order less or equal to 2 extend continuously to the closure of omega. Okay, and for such a function, now we apply, now we look, we apply the divergence theorem to the function, to the vector field x going over to v of x times gradient u of x. Yeah, then the divergence of this vector field, divergence of v times divergence u. I omit here now the arguments. This is by the Leibniz rule. Of course, this is divergence v times divergence u. Yes, scalar product. So here we should also take the divergence of this vector field. So this is scalar product plus v times Laplace u. Yeah, yeah, because divergence of divergence u is clearly Laplace u. Okay, so we have this, and now the divergence theorem tells us, so we get integral over omega. Yeah, we assume, of course, that that omega obeys the conditions such that the divergence theorem applies. Maybe I should make a remark. Yeah, we have shown the divergence theorem for domains omega whose boundary are submanifolds, so continuously differentiable submanifolds. But there exist extensions. Yeah, one can prove this from more general situations. And so instead of saying that the boundary is continuously differentiable, I say that that the divergence theorem holds for the open subset omega. Okay, so we have dv scalar product du here. Maybe I put in now the arguments, yeah. Y, this is equal to the boundary of omega. Okay, and now we should take, of course, v times gradient of u of z. We write of z times n of z d sigma of z. Sorry. Yes, yeah. So this is Green's first formula. Sorry, I of course forget the second term. Yeah. So we get yeah. Maybe let me write it here. Yeah, I forgot this term, of course. Yeah. So we have integral omega v of y Laplacian u of y dny plus this term here. This is equal to this term. Yeah? This is called Green's first formula. Now we subtract the same formula where we replace, where we interchange u and v. This term here is symmetric with respect to u and v, so this cancels if we antisymmetrize. Yeah? Now we take the same formula, interchange v and u, yeah, then we have this here with u and here with v, and here this is the same, and here u and here v. And then we subtract, And then we get second Green's formula. Yeah, so this is an immediate consequence also of the Green's first formula. Okay, and now we apply this Green's second formula. Also, we apply Green's second formula to the situation V is phi of y minus x, or x minus y. It's symmetric, it doesn't matter. So phi of y and u and u of y is equal to u of y. Yeah, so this we don't just. Okay, and then you should keep in mind that phi, since phi has a singularity, phi, to make it clear, as a y mapping to has a singularity at y equals x. So we replace, like in the proof of the solution of Poisson's formula, we replace omega by omega small ball of epsilon for small epsilon, and then take the limit, epsilon going to 0. Okay, and then we already know, also then we have, okay, then we have here the boundary terms, yeah, sorry, we have these two boundary terms, yeah, for in the second form. So we have v times du, also so here phi, this term times du minus u times gradient of phi. And exactly these two terms we already had in the proof of where we constructed the solution of the initial value problem. Yeah, let's recall this moment. Here, fundamental solution, and then we wrote down here are these terms. So this term here, this is also with here this, yeah, so this is this boundary term L epsilon, which is exactly of the form where phi times the gradient of a twice continuously differentiable function, and we showed that this goes to 0. Yeah, so L epsilon here we showed this. Here we showed this. Yeah, this goes to 0. Here one sees this. So L epsilon goes to 0. Yeah, so this term goes to 0, and then later here now we had this term where the derivative, the gradient acts on phi. Yeah, and then this is K epsilon, and then we showed that K epsilon converges to this term. Yeah, and now we apply the same arguments. We may apply the same arguments. Sorry, let's go back now. We are here, green function. So we apply the same arguments here. Yeah. So we have this, these two terms. Also, we have on the one side the term, sorry, here, second. So on the one side we have the term where phi times gradient of u. This goes to 0 if we take the boundary over this part, yeah? Then this goes to 0. Also, yeah, maybe first I should explain. We have that the boundary of omega, yeah, how this looks like. Maybe I draw a picture. We have here omega, we have here x, and then we have a small ball bxl. And this is the ball bx epsilon. Epsilon should be, of course, small. So we look for this domain here. And the boundary, yeah, this is, of course, the boundary of omega. And then what is this boundary? This is the boundary, and I write the boundary of Rn without the ball bx epsilon. Okay, we could also write this is as a set the same as the boundary of the epsilon ball, but the inner norm, the outer normal, this goes here outside, yeah, this would be different. So for this reason I write it in this form, yeah. The outer normal for the epsilon ball would point here inwards, but we want the outer normal here. So we describe it as this. As a set, this is of course the same as the boundary of the epsilon ball. Okay, we have these two parts. Yeah, and the integrals on this part we just write. But in the limit epsilon goes to 0, yeah, this part more or less disappears. It shrinks to a point. So we want to control this part in the limit epsilon goes to 0. Yeah, and we have shown these arguments, which I showed at the beginning. This shows that this part here, phi, here v is the phi, translated by, times gradient of u. But this is a C1 function. This goes to 0. Yeah, on the boundary here, this goes to 0. And this part here, yeah, here it's written, this part here, now we have exactly this boundary over this part, and there we proved this converges to u of x. This converges to u of x. This is exactly the same argument. Yeah, this is exactly of the form which we had before. Yeah, here, this. We have to evaluate this at 0, and if we at z equals 0, and this is u of x. Yeah, this is exactly the same argument which we had before. Okay, yeah, and then we get this. Yeah, and the other term on this boundary vanishes. Furthermore, yeah, on omega without the epsilon ball, x epsilon, Laplacian of phi is 0. Yeah? This is the main reason why we put in, why we subtracted this set, because to get rid of the singularity at y equal to x. Okay, so yeah, to make it more precise, I write it more explicitly. We have Laplacian with respect to y of phi of x minus y is 0. Okay, so now we insert, so second Green's formula. Yeah, so we insert second Green's formula. So we have this term. This term we just write. Yeah, this term we just write. This is exactly this term here. This term we write. This term this term vanishes. Yeah, since v is phi and this the Laplacian vanishes. So this term vanishes. So for this term we get the boundary terms at omega, but no boundary term at this boundary part. Here, this vanishes in the limit epsilon goes to 0. But this term here, this goes to u of x. Now we bring it to the other side, and we have u of x are equal to these two terms and minus this term. And this is now exactly this Green's representation formula, where we inserted that v is equal to phi. So this gives us, now we have proven Green's representation theorem. So the assumption is u is a function twice continuously differentiable on the closure of omega in the sense which I mentioned before. Omega is bounded and open, and the divergence theorem should hold for omega. And then we have this formula. Okay, now this formula, this helps us, this means, by Green's representation theorem, u is completely determined by, what is the data what we need? We need Laplace u on omega, then we can insert this here. Then gradient set of u of z on the boundary, and here u of z on the boundary. For this reason, it's natural to ask for boundary value problems. So if we fix the values of u and gradient u on the boundary, then the Poisson equation minus Laplace u is equal to f. So this means this expression is minus f, has at most one solution. Okay, for this reason it's natural to ask for boundary problems, but we restrict the conditions further. Now there's another observation. By the weak maximum principle, the solution of the so-called Dirichlet problem So this means the following. Again, we have minus Laplace u is equal to f, and u restricted to the boundary is equal to some given function g. Is unique if it exists. Now, why this is the case? Why this is the case? Now, in fact, the difference of two such solutions they obeys du is equal to 0 and u restricted to the boundary is also 0. So it's harmonic. Yeah? If we have two such functions with both or by this, then it's harmonic and vanishes on the boundary. Yeah? But now by the weak maximum principle, this implies u is equal to 0. Yeah? First, it implies that the maximum is 0, and since minus also obeys this equation, then also the maximum of minus, so the minimum is also 0. Maximum and minimum is 0, so it's identically 0. Yeah, this for yeah. So for this reason, now we restrict to the Dirichlet problem. Yeah? Because now we have a real chance if we can show the existence of a solution of the Dirichlet problem for a function g, then we know that there exists exactly one such solution. Yeah, so the idea is, the hope, yeah, the idea is to construct or to establish a one-to-one correspondence, yeah, one-to-one correspondence, one-to-one correspondence between solutions of the Poisson equation and boundary values. Yeah, because then we have a nice parametrization of all solutions. Yeah, this gives a parametrization of all solutions, and this is of course nice. This is the maximum we could obtain. Yeah, at least this is very, very good. Yeah, and now we shall see. Let's see that we can prove, establish this one-to-one correspondence with the help of a so-called Green function, of a Green's function. So this is now a new concept. This is a new concept, yeah, which gave the name for this section, yeah, because it's a very important concept, and this we want to explain now. As first we first define Green's function. Yeah. Then we explain how to solve Dirichlet's problem. With the Green's function. And finally, we construct Green's function for balls. Yeah, that we, at least for balls, solve Dirichlet's problem. So this is the rest of the program of this section. Yeah. Okay. Now let's come to the definition. Here is the definition of Green's function. So here is Green's. A function on the Cartesian product of omega with itself to R, a real function, is called Green's function for this open domain if it has the following two properties, only two properties. First property, for any x, so we've fixed the first coordinate and now consider this only as a function on the second coordinate. Then this Green's functions minus the fundamental solution is harmonic on omega. And second, this Green's functions extends continuously to the boundary and vanishes on the boundary. Yeah? Also for any fixed x on omega, this extends continuously to the boundary and vanishes on the boundary. These are the two conditions. Yeah? So these are the two conditions. Okay, now we want to see what does this help. Yeah? Now we apply as a v of y is equal to g omega of xy minus phi of x minus y. Yeah, for fixed x in omega. For fixed, this is a harmonic function. Yeah, this is a harmonic function, and now we apply second Green's formula. Yeah, for this function. Yeah, we just apply second Green's formula for this function, and then we write all the terms. Yeah, okay. So we get the terms with the g and we get the terms with the phi. We first write the terms with the phi. Yeah, and one should keep in mind that the Laplacian, this difference is really harmonic. So this means Green's function itself and phi, they both have singularities if y approaches to x, but the difference extends continuously and is harmonic. So we get no contribution of the Laplacian, neither from phi nor from g, because the difference of both terms, the difference is harmonic, and so if we insert the difference and then insert in Green's second formula, then this vanishes. Yeah? So we only get the terms where the Laplacian, here is Green's second formula. Yeah, so this term, this vanishes. So we don't get this. Yeah, so we only get these terms on the left-hand side, and yeah, so we get the terms for this and this. We first write the terms for this. Then by a minus we have this. And then we have these are the only term with this term. Yeah? And on the right hand side, of course, we have the corresponding terms with the derivatives. With phi, this is v. And here this represents v with a minus. So yeah, so we put it on the left hand side, and on the right hand side it's with a minus. Yeah, on the right hand side, sorry, second Green's formula, you see here it's this expression, if phi is V is equal to phi, but with a minus, since V is equal to minus phi. Yeah? And here it's with a plus, since V is equal to minus phi. Yeah? And then we put it to the left hand side, so we get these three expressions. Yeah? This with a plus and this with a minus. Okay, so these are the expressions which come from this, and now we write down the corresponding expressions for this expression. Yeah, and then we get no expression with Laplacian, yeah, because this vanishes, and we get and on the boundary G vanishes, so there also is missing the term where we integrate gradient of u times G on the boundary, because on the boundary G vanishes. Yeah, so this term also simplifies. And now this term here, this term is just u of x by Green's second formula, yeah, by Green's theorem, yeah, by Green's representation theory. Here, this sum, yeah, these are exactly these three terms. So we get u of x is equal to this term and this term. Yeah, and this is very nice, because now we really see that, yeah, this formula now shows us that u is completely determined by the data which enters in the Dirichlet problem. Yeah? So here we should replace this by minus f. So instead of the minus, we write here f and get this, and this should be g. Yeah. So we know that if we have a solution, yeah, then it obeys this equation. Now it's very natural to ask, maybe, yeah, so does this formula gives us the solution? Yeah, does the formula obtained by Green's representation theorem gives a solution of Dirichlet's problem what we know is, we know that this is the only possible solution. Yeah, of course, if the domain, maybe we should write this. So if the domain obeys the conditions, for the domain the divergence theorem holds, and if the function u has enough regularity such that all these integrals exists. Yeah, the condition is if omega fulfills the divergence theorem and u has enough regularity. And what this explicitly means, this depends on the domain. And we will carry this out only for balls. Yeah? We shall prove this for omega when omega is any ball later. Yeah, but at the moment, in general, we present a strategy. How to prove that this function u, yeah, which is given here by this formula, that this function solves the Dirichlet problem. So maybe I should say for which functions, yeah, which conditions we need on f and g, yeah, more precisely for given omega. Yeah, the question is for which functions f omega going to R and g boundary going also to R, the function u defined by the formula solves the Dirichlet problem. And this we will answer only for balls, yeah? Because this really depends on the Green's functions, on the existence of the Green's functions, and so on. But let us make one more remark. How one can find, yeah. Now, but all together, yeah. Okay, so all together, yeah. But in general, the solution of Dirichlet's problem reduces to the problem to determine Green's function. And now let me make some remark. Yeah, of course, to determine Green's function is equivalent to determine this difference. But this difference is harmonic, so it solves a very nice boundary problem. Yeah? G omega. So y going over to g omega of y minus phi of x minus y solves the following Dirichlet problem. Yeah, its Laplacian u is 0 on omega, clearly, it's harmonic, and u of z is equal, now look here, at phi of x minus z for a z on the boundary. So this means we need to solve all these special Dirichlet problems, if we solve this special Dirichlet problems, yeah, these are special Dirichlet problems. So the Green's function, yeah, the Green's function is a concept to reduce the solution of the general Dirichlet problem to the solution of special Dirichlet problems. Namely, we only need to find the harmonic functions on omega whose boundary values are given by the fundamental solution. But of course, the family is parameterized by x. Okay, this is now the general remark. And then now it remains to do two things. Now we will prove a general theorem about the Green's function, yeah, and then we determine Green's functions of the unit ball. Yeah, this is what we do to what remains to be done today in this lecture. Sorry. Okay, and first, very important theorem is symmetry of the Green's function. So if there is a Green's function for the domain, then it's symmetric for all x not equal to y. And the proof is quite simple. Yeah, we have our domain omega. Now we have 2 points, x and y, 2 arbitrary points. But they should be non-equal. And then we choose small balls, small disjoint balls. Yeah, and then, yeah, because the Green's function has singularities. Yeah, at these two Green's functions, yeah, they have singularities. If here this has if x is equal to y, or if y is equal to x, so we have this two Green's functions, yeah, and so we remove this, and then we do the following, yeah, then we look for this u of z is g of x z, and v of z is g of y z. Y has a singularity v has a singularity at y, and u has a singularity at x. And then we just insert Green's second formula. Yeah, and on the complement, we know that u and v are harmonic. Yeah? U and v are harmonic by definition of the Green's functions. Yeah, so we only get boundary terms. We only get the boundary terms. And here we have written all the boundary terms. We write them in such a form that we have the boundary terms at the boundary. We have no boundary terms at omega, but at omega, one of these functions, both functions vanishes. Sorry, at the boundary. Yeah, at the boundary of omega, both Green's functions vanish. So we get no boundary terms at the boundary of the omega. So we get only the boundary terms here of these two balls. And at this ball here, yeah, only this function has a singularity. Yeah? This function here has no singularity, is smooth there. Yeah? And for this reason, and G differs by a harmonic smooth function by phi. So this term behaves nearby x exactly like if we write here phi, if we now take the limit epsilon goes to 0, if we replace here this by phi. Yeah, so if we replace this by phi, then, and we should also replace this by phi. Yeah, and the other term, as a G, is of course harmonic plus phi. Yeah, you should also consider, so G of x z minus phi of x minus z is harmonic, and G of y of z minus phi of y minus z is also harmonic with respect to z. Maybe I should write this in this form. Yeah, these two are harmonic and they are smooth and so on. So for these terms, yeah, we can for this difference we can immediately take the limit when epsilon goes to 0 and get no contribution. Yeah, so here and this means nearby x, this term here, this we should replace by this term in order to determine this limit, and in this term we should replace this and then take the limit. Yeah, and here vice versa. Here this term has a singularity at y, this term, so we should replace this by phi and replace this by phi. And then by the same arguments as before, yeah, we know if we take phi times a continuous function, then this limit goes to 0. So this doesn't contribute if we take the limit epsilon goes to 0. And this term also doesn't contribute by epsilon. And the same arguments also apply. Here we get just the limit if we insert z equal to x. Yeah, here we get the limit inserting z equal to x. But this means this converges to g of yx. And here this term, here at this term, this here diverges, but here we should insert z equal to y at the singularity. So we get g of xy. So in the limit epsilon goes to 0, here gets no contribution, here this goes to 0, but this converges to g of yx and this converges to g of xy. And then this equation shows the equality. So this is the proof. So it's just an we observed that we can again take the same arguments as in the first lemma where we established the initial value problem, and then by the same methods, by these limits, yeah, we really obtain this. Okay, this is now we know Green's function is symmetric. This of course means that the Green's functions now considered with the other argument is also harmonic. Yeah, okay, so this has strong consequences. And now we determine the Green's function for the unit ball. Yeah, now this is now the last step. Now we determine Green's function for the unit ball. And this is very simple. Yeah, we use some trick. So we have here the unit ball 0. This is the boundary of the unit ball. And if we have some point x here, yeah, then we consider x tilde, which should be x divided by x length square. Yeah, x length square. Then, of course, the length of x tilde is, so it's 1 over x. So if x is inside the ball, then x tilde is outside the ball. And if x has length 1, then x tilde has also length 1, and you see directly, and x tilde is equal to x. So for this reason, yeah, if it's on the boundary of the unit ball, then this x tilde is equal to x. So the map x mapping to x tilde is a reflection along the boundary of the unit ball. Yeah, also if we have this vector x, the other vector sits on the straight line, yeah, because we only rescale it. It sits on the straight line here going from 0, but the length is the inverse of the length. Yeah, so here this is reflected to some point on the outside with inverse length. Yeah, so this is smaller than 1, then the inverse length is larger than 1, and so on. And of course, if we do it twice, we come back, yeah, because the inverse of the inverse is the same again. Okay, so this should be considered as a reflection along the unit sphere, so the boundary of the ball. Okay, and now we do a simple calculation. Now we claim that x absolute value times x tilde minus y is equal, we claim, yeah, that this, no, sorry. We claim that x tilde minus y is equal to x minus y if y has length 1. Let's do the calculation. So to prove this, yeah, so we prove that this new coordinate is the same as this coordinate if y has length 1. So why this is the case? It suffices to show, yeah, of course, because no, sorry, we want to prove something else, some weaker statement. What we want to prove is that this is the same. Of course, it suffices to show that the square, so it suffices to show x square, x tilde minus y, and whole thing absolute square is the same as x minus y square if y has length 1. Okay, let's do here the calculation. What is this? Okay, this is of course x squared times, and now we have what is the square? So this is x tilde minus y square, and this is the same as x squared times. If we multiply this out, this is x squared minus 2 times x tilde times y plus y squared. Okay, and sorry, here x tilde square. And now x tilde square, yeah, is of course the same as x square we have. Now x tilde square is x square by x square square, yeah, because x tilde was here by this. Okay, so we have this minus, and then we have 2 times x times y divided by x square plus y square. Now we may write this in, and we know that this is 1. So what does this gives here? Yeah, 1 square cancels, so this is x square. here this cancels, minus 2xy. And here we get y squared is 1. So we get, sorry, no, here we get 1. Yeah, 1 we get here. Yeah, x squared times y squared, this is 1. Minus xy, and here we get plus x squared. Okay. And now, so this is the left-hand side. And now let's calculate the right-hand side. X minus y squared. Yeah, this is of course x squared minus 2xy plus y squared. And this is of course x squared minus 2xy plus 1. So we see indeed these are equal. Yeah, so this simple calculation shows that this is equal to this. And for this reason, yeah, if y has absolute value 1, so if we are on the boundary of the unit ball, then these two terms cancel. Yeah, these two terms cancel, and now we use the explicit formula for phi, yeah, the fundamental solution. And if we use the explicit formula for phi, then we see it looks like this. Yeah? This is just phi is, also for n, maybe we call it. So here it's the formula. So it's minus some constant times ln from x absolute value, and it's some constant for n equals 2, and otherwise it's some constant times x absolute value to the power of 2 minus n. Yeah. So if we multiply the argument, yeah, then if we multiply the argument, then we get then for n equals 2, it's 1 divided by this expression here. Yeah, so if we take this product, then we just get this factor. Yeah, and the logarithm of a product is the sum of the logarithms. For this reason, for n equals 2, we get this. On the right-hand side, now you see that as a function of y, since this is harmonic, yeah, then if we multiply it by some constant, it's also harmonic. And since this is harmonic, yeah, this is only a constant as independence of y. So this is harmonic, and it's harmonic on the whole unit ball, yeah, because the singularity now sits outside. Yeah, x tilde sits outside, so the singularity of this function sits outside, not anymore inside the unit ball. So by this trick, we determined the Green's function of the unit ball. Yeah, also by this calculation we see both properties. We see first it vanishes if epsilon absolute value is 1, because then these two terms are equal and cancel each other, so it's 0. And by this formula, we see as a function on y, this is harmonic on the whole unit ball, yeah, because the singularity sits outside, and this is also harmonic on the whole unit ball. So it has exactly the properties. Yeah? If we subtract this term, then it's harmonic and it vanishes on the boundary. Yeah? So this is now Green's function, and we have determined Green's function. Okay, here we finish this video. Let's recall what we have done today. Yeah, we introduced first Green's first formula, Green's second formula, then obtained Green's representation formula. Then we understand by Green's representation formula that we should look for some boundary value problems. Yeah, if we want to solve the Poisson equation, it's enough to give the values of u on the boundary and of the gradient of the boundary. Yeah, okay, so this gives general boundary value problems, and then but we also understood we can use the weak maximum principle in order, and then even the Dirichlet problem is unique. Yeah, so we formulated the Dirichlet problem, and then we introduced the concept of Green's function, and derived this formula, and understood that due to this formula, the knowledge of Green's functions gives us solutions of the Dirichlet problem if the functions are nice enough. Okay, and what means nice enough? This depends on the special properties of the domain and the Green's functions. And then we understand that to solve the Green's functions means just to solve some special Dirichlet problems. So the whole method of the Green's functions should be understood as to reduce the general Dirichlet problem to special Dirichlet problems. Then we showed symmetry of the Green's functions, and finally we determined the Green's function of the unit ball. Thank you.